Hi everyone, welcome to ELEC 2507 Lab 1. I'm Adam and I'm going to walk you through what to do here. So basically the first step that I'm going to get you to do is, if you haven't already downloaded the VPN, go ahead and navigate to this site right here. That site will open up a list of different platforms that you can download the VPN for. In my case it's Windows 10. I'm going to go ahead and navigate to cvpn.carleton.ca and I'm going to log in with my CLearn username and my password for CLearn as well. So once I've done that, click login, it'll pop up a download link, and I can go ahead and install that on my local machine. And then once that's done, I can go ahead and go to the system tray here and type in Cisco AnyConnect. And I'll hit connect, and my username is, again, my CLearn username, and password is the same one that you just put in. So go ahead and accept that you're aware of all the privacy concerns related to the Carleton VPN. Hit accept. And then once your connection is established, you'll see a little pop-up link that shows that you're connected to the VPN. So the next step that I'm going to get you guys to do is look at the remote desktop connection. Okay? So either you're on a Mac and you're going to have to download the remote desktop app, or you're on a Windows PC where you can just go into the system tray and type in remote desktop connection and open it up. But another way to do it is just by going to the lab stats page. You can go here and looking at your assigned station. So go back to CLearn, go to the ELEC 2507 course, and you'll find lab general info, right? And the lab master groupings list has everyone's assigned station as well as their lab grouping. So Michael Issa, you're assigned station number 4, and so on and so forth. And those station numbers are also assigned a different value for your R3 resistor in this lab. So if I'm assigned station number 4 again, my value for R3 is actually 1,220 ohms. So I'm going to use that in my pre-lab calculations and in my lab simulations as well. So in my case, I'm actually working on computer number 1. So I'm going to go ahead and download the remote desktop connection for computer number 1. So I see ME4195, computer number 1, and I'll click download. And what that'll do is just download another remote desktop connection for me. I've already got it downloaded a couple times, so I don't need to do that right now. So once you have that in your downloads folder, go ahead and double click on it. It should open a window that looks something like this. And you go into more choices, and we're going to connect to the VLSI server, so VLSI / not backslash, and then again your CLearn username, and your password here is small p, capital W, and then your student number. So I'm going to go ahead and click remember me, so next time I log in, I don't have to do any of this. It'll remember all these credentials for me. And because these will be your assigned stations for the whole semester, you can just go ahead and save those credentials and actually save that connection file wherever you like. So the next thing I'm going to get you guys to do is actually navigate over to CLearn. So go to CLearn. And you're going to go ahead and log in there. And you're going to scroll down until you find the Lab 1 info. And Lab 1 info should have the Multisim files as well as the MATLAB file and the resistor list. So I'm going to go ahead into that folder and click download folder. Ugh. So that should pop up in my downloads folder, but downloads folder isn't really great for saving your work because it'll get deleted every time you log out. So you're gonna go ahead, open a new window, go to your H drive, and actually create a folder for this course. So I've already created one, but I'll go ahead and recreate it. So I've created a 2507 folder, and I'm going to drag and drop my files that I've just and I'm going to uncompress them. So now that these files are in my H drive and they're uncompressed, I can actually use them. And now we see that we have a lab bode plot script that we can use at the end of the lab. We actually have the simulation files for the part 1, part 2, and part 3. So now that all the kind of triaging steps are out of the way, I'm going to get you to go ahead and actually finish your pre-lab if you haven't yet, because what you're doing in this lab is mostly verifying a lot of the values that you get in the pre-lab, so make sure you've already done that before you start. Your R3 value, again, as I showed you, is denoted by that resistors list here. So if I'm on station number 1, my resistor value is actually 1K. If I'm on station number 11, my resistor value is actually 2200. So I'm going to go ahead, and the first thing it asks me to do in the first part of the lab is actually open up the 4P1 and 4P2 file. So I'm going to go back in, I'm going to open that one up. It then asks us to remove the connections for the DC supply. So it says in Multisim, it simply means disconnecting the wires that connect the input source to the rest of the circuit. So we're going to go ahead over back to Multisim, and we're going to delete these just 2 wires, just like that. Okay, so the next step it actually asks us to do is we're going to use the multimeter within Multisim, and we're going to measure the input resistance at the VN port, okay? So we're going to remove the load as well, and we're also going to remeasure the input resistance. So we're going to measure the input resistance with a load and without a load. So you're going to mark those 2 values down for your report. So go ahead and click Run there, and you're going to click on the input multimeter here and switch to ohms. And you should see a value for your input resistance here. That's with a load connected. So go ahead and stop the simulation again. Now we're going to delete those 2 wires for the load, so now the load gets disconnected, right? And we're going to run the simulation again. Reopen the multimeter and see that our input resistance has now changed. The last step here wants us to remove our L, which we've already done from the previous step, and short the input terminals together by placing a wire between both nodes of the input port. So if you hit Control-Shift-W on your keyboard, that should bring up a wiring command where you can actually just place a wire around the circuit. Oop. Go ahead and clean that up a little bit. All right. Now that our input terminals are actually shorted, right, we can go ahead and run this simulation once more. And now we can open our output terminal. And our output terminal is now measuring our output resistance, right, because our input terminal is actually shorted. So I can see that I have a certain value here for my output resistance. And this should correspond to something that you calculated in the pre-lab. So go ahead and go back to the document, and you can explain any differences between the measured values and the corresponding pre-lab exercises. So in the pre-lab, you should have measured VN with and without a load, and you should have also calculated the output resistance of the circuit, and they should be somewhat similar to what you actually found in Multisim. So go ahead and compare those values and notice any differences. So the next step of this lab asks us to measure transfer functions. So we're going to actually connect back the DC power block by reconnecting the wires that we just disconnected. And note that the load is not yet connected, so we can keep the load not connected for now. So go ahead and stop that simulation. And I'm going to actually delete this short that we created. And now when we're just on the end of a component, a little wiring thing will actually get brought up, as you can see here, and then we can just drag it over. Just like so. So as you guys can see here, there's a 50 ohm resistance on the actual source, right? Source voltage. So there's going to be a small voltage divider between here and the rest of the circuit. The rest of the circuit's input resistance, right? And that this resistance here is going to be much, much larger than 50 ohms. So the drop across this resistor is almost going to be negligible. It'll be probably maximum of around 0.3 volts or something like that. We're not going to get the whole 5 volts here, but we're going to get very close to it, okay? And that's what this section wants you to notice. So go ahead and run that simulation once more, open the input multimeter, and check the voltage, and see that I have 4.771 volts right now on my input terminals, which makes sense, right? Because I have a somewhat large resistance here of around 1K, let's say, and the resistance here is only 50 ohms, so I have a very, very small voltage divider, and the drop across here is almost negligible. So now it wants us to use the multimeter within Multisim and measure the voltage at both ports, so the output and the input port, and measure the voltage gain, which is V out divided by Vin. And then we're going to actually refer to the pre-lab again and say what these measurements correspond to. So I have 4.771 on my input. I'm going to open my output multimeter right now, and I hit volts, and I can see that I have a certain amount of voltage on my output right now, right? So this value should be very close. When you go V out divided by V in, it should be very close to what you calculated in the pre-lab with the unloaded condition. And then next, it wants us to connect a 220 ohm load resistor, and then measure the voltage at V out once again. So it wants us to measure the voltage gain, V out divided by V in, once again. So we're going to go ahead, stop that simulation so we can reconnect the wire, okay? And then go ahead, just go to the end of the component once again, and wire it up, just like so. And once you've done that, you can go ahead and rerun the simulation. The multimeters are already open, so these values should change. Only slightly though, right? So this value, as you saw, changed slightly because the input resistance as seen by this terminal is changed ever so slightly by this load resistance. Not very much, but ever so slightly. And same with the output. The output resistance is actually much different because now we have a load of 220 ohms rather than an unloaded condition, right? So we're going to explain why that gain with a load is actually lower than without a load. And then we're going to repeat the simulation using a 120 ohm load resistor, and then again note why it's lower than the 220 ohm case. So let's go ahead back to the simulation and we'll open up RL, okay? And just double clicking on RL opens it up and hit OK. If you actually change any values while you're running a simulation, as you can see here, it'll come with this pop-up and say the simulation is running, and any changes you made in the design will not take effect until the restart of the simulation. So hit OK, just hit stop and then hit restart, and that should change things up. So now I can see that I have a different output versus input voltage, so do V out divided by V in once again, and you can notice the voltage gain once again actually decreases. So the next section actually says, it's a little bit complicated, but it says that in 4.1.6 you measured the open circuit voltage because the input resistance of the multimeter is much, much greater than the circuit's output resistance, right? So what we're going to do now is using that as V Thevenin. So V open circuit is the same as V Thevenin, right? And then we are also going to measure I short circuit by connecting V out to ground. Okay, so just placing a wire between the V out node and ground. And then we're going to measure the voltage drop across R2, right? And then if we do V over R, we can actually have a value for ISC, which that's in an actual lab scenario. In this case, we're going to use a probe, which is just a current probe, to measure the current through R2. So once you're back in the simulation, go ahead and stop it for now. And then you're going to hit Control-Shift-W again to place a wire, right? Because we want to short the output. So we want to just place a wire between those nodes, just like so. And once we have that in place, we can go ahead and rerun the simulation once again, and just put, I don't know if you guys saw that, but I put what's called a current probe here. So the A signals current, and I can see that I have a certain amount of DC current running through that branch, and that is virtually my I short circuit. So I have a V open circuit, or V Thevenin, from 4.1.6, and now I just measured I short circuit. So with that, I can find a value for the Thevenin resistance, right, based on my measurements, and the Thevenin resistance will be used to actually create the Thevenin equivalent in 4.2. So once those things are done, let's go ahead and actually stop the simulation once more, because we're now on to 4.2 and we're creating a Thevenin equivalent. So we need to go over to this little pad over here. But we want to actually translate a couple of these components. So VS, we want. $1.2 is fine. We'll switch the value over here. And we want the load resistor as well, right? We also are going to need a ground node for this whole circuit. So once you have copy and pasted all four of those elements in, you have all the elements that are needed to recreate this, this circuit into a Thevenin equivalency. What we're going to do is go ahead and change the values of all of them. So here we actually need V Thevenin, right? So it's not 5 volts, it's whatever you calculated as V Thevenin. So in my case, it's 1.403. And your R4 value is actually R Thevenin, right? So in my case, my R Thevenin was around 357 ohms, so I'll put that in there. And I can go ahead and connect up the circuit, just like so. Once that's all connected, the last thing we need is a multimeter, right? Another multimeter. So go ahead and actually click on the top right here in multimeter, and you can hit Control R to actually rotate that multimeter. So go ahead and place it somewhere out like there. And that should be fine. Go ahead and clean those up if you'd like. Alright, so now that that's done, we can go ahead and rerun the simulation now. And all we're looking to do is replace this with a 220 ohm load to start. And we're looking to verify that we get the exact same things on, well, approximately the exact same value with this whole circuit with the 5 volt source and this input impedance as seen looking from this side, and this Thevenin equivalent circuit over here. So go ahead and run that circuit. And we can open the multimeter for over here, right? And we can see we have 535 millivolts. So if this Thevenin equivalent is holding true, we should have approximately 535 millivolts on this multimeter as well, which is true. What do you know? So that means the Thevenin equivalency is holding there, and we do have a Thevenin equivalent circuit. So let's go ahead and switch that to a 120 ohm load resistor. And do the same over here, just to kind of see them both at the same time. And check the output multimeter here. So we have 352 millivolts. And we have 352 millivolts, around 353 actually. But very close on both the multimeters in both of these configurations. And that's with 5% tolerances on all the resistors except for the load and the source resistor. So here you're going to compare the voltages that you found in the previous section with those found in this section here, and you're going to explain any slight discrepancies and why they might be so. So go ahead, and the last portion actually asks us to open, before we get to the hardware measurements, asks us to open up the 4P3 file. And it says, note that we are not attaching a load resistance to the amplifier in this experiment. In other words, the amplifier is unloaded. So let's go ahead into the folder again that we created, and we're going to find the 4P3 file, and go ahead and open that one up. And make sure you have your previous simulation stopped. If you don't, it won't let you run the next one. So the first step here asks us to actually switch off the AC supply. So switch it to 0 volts peak and set the offset voltage to 5 volts DC. And then we're going to measure the transfer function once again. So let's go ahead and let's go back to the simulation. We're going to switch that to 0 volts AC, right? And a 5 volt DC offset. And then we will go ahead and we will run that simulation. And actually, to see the output voltage here, right, we're going to place a probe. So again, you could place a multimeter, but in this case, I just like to place a probe. So if you go up here and place a voltage probe, place that right there. And you can see you have 0 volts DC, right? And you have a 5 volts DC on the input. So the transfer function is 0 over 5, which seems a little odd. I don't know. You have some explaining to do, I guess, in your lab report. Let me know why you think that's happening. Is the result expected? If so, explain why. Yeah. The next step is asking us to set the voltage offset back to 0 volts. So we'll go ahead and set the offset to 0 volts. And it's asking us to set a 2 volts peak to peak, right? And in this case, we're looking at voltage peak. So if we want a 2 volts peak to peak, we want a 1 volt peak amplitude. So the next section asks us to connect the bode plotter in Multisim, connect the V-in port to VI, and connect V-out to V-out. Find the voltage gain of V-out over V-in and phase difference between the two signals. So this is done using just the bode plotter functionality directly in Multisim. So these nets are actually connected via like these things here. So you can go ahead and just run that simulation as long as we have your output set properly and that. And you can look at the bode plotter and you can actually reverse the magnitude if you want to look at a white background versus a black background. And this is just for exporting your plots in Multisim before you put them in your lab. So the smallest value is actually 1 millihertz here. What you're going to do is you're going to have to extrapolate backwards and find out what the gain in dB and what the theoretical phase difference would be at 0 hertz. There's no actual tool that can measure at 0 hertz, but it's a theoretical gain and phase that you're going to have to calculate there. So go ahead and take your table of values. So I've given you a table to fill out. So you're going to fill out this table for 0 hertz, 10 hertz, 100 hertz, 1 kilohertz, 10 kilohertz, 100 kilohertz, and 1 megahertz. So there's 7 different values there, I believe. And you're going to fill out this table for your input voltage, your output voltage, your phase angle, and your gain. And your gain is just given directly on this plot right here, right? So you're just going to go scroll along, find your gain. You know the magnitude of your input is always 2 volts peak to peak. And you know, you can extrapolate backwards to fill in all the columns of that table. So as long as you fill in this line and this line and this line, you can extrapolate back to find this line and this line as well, doing that. Okay, so you're going to take different values. So you're going to take one at 10 hertz. When I say you're taking a value at 10 hertz, don't worry about having it extremely precise. Within a margin of error is okay. So let's find a value here just to show you. So like 10.195 hertz at 50.5, negative 50.5 dBs, let's say. You don't have to be within 4 decimal places, so I don't care. But as long as you're fairly in the ballpark of the 10 hertz range, just so you get a nice looking graph like such, right? Yeah, so same with 100 hertz, 100 hertz may not have a value. Yeah, 98 is probably the closest value there. So go ahead and take that value and mark that in your table, and that should be fine. Make sure you're exporting both of these plots for your write-up. So don't take a screenshot of everything on the page, like including all this. Please just take this part. That's the only pertinent information that I care about, and your TAs will care about when they're marking. So, and last but not least, it asks us to repeat these measurements in a hardware setup. So the hardware station has already been configured for you. So there's a camera and everything, so you can actually view the circuit that you're working on at the moment. You don't necessarily have to do that, but it's just useful for your own learning. So let's navigate to Firefox. Make sure you navigate to Firefox and don't just double click on the scope straight in the desktop. So don't just double click on that link. Just go in, right click on it, go into properties and find the link for your actual scope. And then navigate to Firefox and paste and go. There's an error if you open it in Edge, so it'll sometimes close your remote connection and freeze up your remote connection, and it's a pain. So if you get a request timeout, that's fine. Just go ahead and click refresh, and the page should show up for you here. All right. So we see that channel 1 is connected on our V-in, and channel 2 is connected on our output, right? Just as we had in the simulation setup. So now you can navigate to the scope's bode plot function using the app selection menu seen in the figure below. So we're going to go ahead back to the scope and go to the app selection menu, which is on the bottom right. And then go to bode plot. Bode plot's right here. And once you're there, you can actually set all these parameters, right? So what I'm looking to do is I'm looking to recreate the simulation setup that we just ran, right? So the amplitude I ran was a 2 volt peak to peak, or a 1 volt peak on the last simulation of Multisim. So I'm going to go ahead and keep that 2 volts peak to peak. I want 10 points per decade. I want to stop my simulation at 10 megahertz, and I want to start my simulation at the lowest frequency, which is 10 hertz, right? And if I do that, then I go ahead and hit run. Then we can see that up here, there's a sweep of the output in the green waveform versus the input, which is the yellow waveform, at different frequencies. So it's taking 61 different points here, and all those points are adding up to create this graph. Once the graph is created, we then see that there's a table down here actually. So this table is actually really useful for kind of recreating what you see on the scope here in a much nicer, easier to view plot. So the way we can do that is actually by navigating over to MATLAB. So go back into the Lab 1 Multisim files folder, and you'll see a MATLAB script. It's called ELEC 2507 Lab 1 Bode Plots. You're going to open that up, double click. You're going to navigate down to the comment where it says low pass bode plot in 4.3. And here's where you're going to enter every single frequency point that you're taking in the table. So you're basically just transcribing this table. So frequency of 10 hertz. I'm going to transcribe my gain and my phase all into column vectors in MATLAB. Okay, so 10 hertz, my magnitude of my gain is negative 50.8. So negative 50.8 work. Make sure you're putting commas after everything, right? And then my phase is 88.66. All right. So I don't think you guys need to watch me fill out the rest of this chart. All I'm going to do is just basically scroll down in this list, fill that chart out with all my different frequencies that were asked of me. So 10 hertz, 100 hertz, 1 kilohertz, 10 kilohertz, 100 kilohertz, and 1 megahertz. And I'm going to fill out that table, and then I'm going to hit run. And it should create a nice looking plot for me that I can export. for my write-up. And when entering kilohertz and stuff like that, make sure you use e to the 3 or e to the 6 to specify megahertz. So once you've transcribed all the values from the actual scope list into MATLAB, you can go ahead and enter a title. So plot So I'm going to go ahead and plot that one, and I can see that I have a high pass response. Okay, so the phase is actually going from around 90 down to 0 as frequency increases, and the magnitude of voltage gain is actually increasing with frequency. And that makes sense because it looks like virtually the same graph that we got here, right? Here there's a lot more points, so it's going to look a lot more fine. But in our graph on MATLAB, it's an easily exportable file, so we can actually go File, Save As, and we can save it as a PNG file. So if we want to save it into the same folder that we've saved all the rest of our files, so our Multisim files and our MATLAB file, right? So we can easily zip those up and send them back to the TA for marking when we're submitting our report. So I'll just go and label this bode plot HPF, meaning bode plot high pass filter, and go ahead and exit there. So now that all your data is taken and everything's ready to go, you're worried about your report. So reports basically should just be concise and just include the required equations and final numbers, along with a brief discussion on each of the experiments you performed. If they ask for a discussion, that is. So think about them as semi-formal reports, including your title page, a brief introduction, and a brief conclusion. Make sure to attach your pre-lab to your report for easy marking. And if you have to upload them as separate files, that's fine, but a singular Word /PDF doc for both lab /pre-lab is preferred. Make it brief and to the point. And make sure you're attaching both your Multisim files, your MATLAB file, and your, just your MATLAB files and your Multisim files as well. If you want to include that photo in the zip folder, that's okay as well. You can do that, but by all means, that's not necessary. So I believe that's all you guys need to know for Lab 1. That takes you to the end of the document. And good luck, and we'll see you back in Lab 2. Bye-bye. Oh yeah, one last thing. Make sure you're grabbing screenshots of these bode plots as well from your simulation files, or else you won't be able to compare them to the bode plots that you got from MATLAB. Okay? And that's the idea here, is you're going to look at both of these different plots, and you're going to compare where they differ and where they're the same. Okay? So again, good luck, and we'll see you again next week in Lab 2. Bye.